The moment your chef knife slices through the outer layers of a raw onion, you trigger a biochemical trap designed over millions of years of plant evolution. Within seconds, an invisible gas wafts up toward your face, your eyes begin to sting, and tears pour down your cheeks. It feels like a targeted attack, and in a very real evolutionary sense, it is. The onion isn't trying to make your soup taste better, it's defending itself against being eaten. To understand why this happens, you have to look at how an onion cell is built. Under normal conditions, an intact onion is completely harmless to your eyes. You can hold a whole onion, peel its dry outer skin, or hold it up to your nose and nothing happens. That's because the chemical ingredients responsible for making you cry are kept strictly separated inside microscopic compartments within each cell. Think of an onion cell as a tiny container holding two distinct liquids separated by internal walls, much like a two-part epoxy resin. On one side of the wall, inside liquid-filled sacs called vacuoles, the onion stores sulfur-rich amino acid compounds known as sulfoxides. On the other side, out in the cell's fluid body, sits a specialized enzyme called Alionase. As long as the onion remains whole and undamaged, these two components never meet. They sit mere micrometers apart in perfectly harmless isolation. When your knife blade crushes and tears through those cell walls, the structural boundaries vanish. The enzyme and the precursor compounds instantly mix together, initiating a rapid multi-step chemical chain reaction. First, the enzyme breaks down the sulfoxides into volatile sulfenic acids. Almost simultaneously, a second enzyme, known as lacrimatory factor synthase, goes to work. It rearranges the unstable sulfenic acids into a specific, highly volatile chemical compound called syn-propanethyls-oxide. This newly formed molecule is light, unstable, and vaporizes easily into the surrounding air at room temperature. As you continue chopping, a cloud of this invisible chemical gas rises directly from the cutting board toward your face. When syn-propanethyls-oxide hits your open eyes, it mixes with the delicate film of moisture that constantly coats your cornea. The cornea is one of the most sensitive sensory surfaces in the human body, densely packed with pain-sensing nerve endings known as ciliary nerves. When the volatile gas dissolves into the aqueous layer on the surface of your eye, it breaks down into a mild solution of sulfuric acid, along with hydrogen sulfide and propananol. Even in microscopic concentrations, sulfuric acid acts as a severe irritant. The ciliary nerve endings instantly detect the sudden drop in pH and the presence of sulfur compounds, signaling an emergency to your central nervous system. Your brain interprets this localized burning sensation as a direct threat to your vision. In response, it fires back a signal through the autonomic nervous system to your lacrimatory glands, the tear-producing structures situated above the outer corners of your eyes. The lacrimatory glands immediately flood the eye with reflex tears. Unlike the baseline lubricating tears that keep your eyes moist day to day, reflex tears are produced in massive volumes, specifically to wash away foreign chemical irritants and dilute the acid before it can cause structural damage to the corneal tissue. The reflex is so powerful that your nasal passages often start running as well, as excess tear fluid drains through the tear ducts into your nose. Knowing the exact chemical pathway behind this defense mechanism explains why popular culinary tricks either work or completely fail. For instance, wearing standard eyeglasses rarely works because volatile gas easily drifts around the lenses. However, airtight swimming goggles create a physical barrier that prevents the gas from ever reaching the eye's moisture layer. Chilling the onion in the refrigerator before slicing is another effective strategy. Cold temperatures slow down chemical reactions and drastically reduce the volatility of syn-propanethyls-oxide, keeping more of the gas trapped in the liquid phase on the cutting board rather than floating up to your face. Similarly, using a very sharp knife rather than a dull one cleanly slices through cells rather than crushing them, fracturing far fewer cell walls and releasing significantly smaller amounts of the reactive enzymes. So the next time you find yourself tearing up over a cutting board, remember that you aren't just experiencing an annoying kitchen inconvenience, you're witnessing a sophisticated, damage-activated chemical defense network, a subterranean bulb's clever strategy to turn a browser's meal into a burning lesson.